Hello guys, welcome to Self-Help Maths Academy. Today we are going to discuss about the column space. Okay, so first let us see what is the column space is all about and how do we deal with the examples on this. That will be our discussion of today. So that is, let me start with the column space. Okay, so basically the column space, let us write the definition first, what the definition talks about it. The column space is the column space of an M cross N matrix. Say capital A. Usually we write it as call A, the column space. It is the set of all linear combinations of the columns of A. That is, if capital A equal to say A1, A2 and AN, then the call A is simply the span of A1 to AN. So let us understand what is the definition says. Okay, to say that the column to tell that it has a column space, what one has to be obeying the different conditions. That's what is the important discussion of today. So in order to understand what is the call space here, the column space of here basically it has to be for any M cross N matrix. So therefore there is no compulsion on the given matrix to be a square matrix. It can be any M cross N matrix A. That is first thing. We can write our column space as call A. As in the previous notation we have seen the null space as written as the null A. This is the set of all the linear combinations of the columns of A. So for example, if I have a matrix A is equal to say 1, 2, 3 and 2 minus 1, 4. For example, if this is our given matrix of 3 cross 3 rows and 2 columns, we have a matrix of order 3 cross 2 here. So the call of this matrix will be the set of all possible linear combination of these columns. For example, as you see, here we have got a column. Here we have got a column that speaks about the linear combination. For example, here I'm going to have a specific column as say this is my A1 and A2. If I consider any linear combination of this columns, say C1 A1 plus C2 A2, where C1 and C2 are any scalars. So set of all possible linear combination of these two columns, we say that as when I say the set of all linear combination of those two columns, it is nothing but a span. So span is nothing but the set of all linear combination of those particular columns. If you see here in this case A1 and A2, so set of all those possible linear combination of those two columns, we call it as call A. So here basically this is a span of these two vectors. If I've taken them as like A1 and A2, then span of A1 and A2 will be our call of this particular matrix. So basically the column space is what? Column space is the set of all the linear combination of those two, the particular columns of the given particular matrix. Okay, so now as we have seen the the properties in case of our null A, here also we have the properties. Let us see what are the basic properties we have in this case. Okay, so in order to understand them in a better way, so let's see one by one. Okay, so here the one of the property it says that it talks about the call space, the column space, the column space of M cross N matrix, the column space of a M cross N matrix A, okay, is a, it is a subspace. It is a subspace of Rm. It is a subspace of Rm. So basically it is nothing but what? Call A is nothing but B such that B equal to Ax. This is for some X in Rem. So we are talking about this collection. It is nothing but what? We are collecting those vectors B, I mean like the collection of all those vectors B such that B is equal to X equal to B, where this is a non-homogeneous equation. Okay, so we are looking for those X which are becoming a solution for this non-homogeneous system of a equation, where X is coming from where? X is coming from Rm. As you know, the given matrix is of M cross N order. Okay, so the number of rows will decide the dimension of the X. Okay, so here if suppose you have a 2 cross 3 matrix, then your X is coming from R2. Okay, if it is say 3 cross 4 matrix, then your X will be from R3, so and so on, so on and so forth. Okay, so therefore the column space of a M cross N matrix is also a subspace of Rm. So therefore we have got now column space is also one of the subspace. It will be a subspace of a Rn. Okay, so we have got an example for a subspace. As we have seen, the null space is also a subspace of Rn. So here we have got a column space is a subspace of Rm. Okay, so now let us see. Let us try to understand this particular definition in detail with the help of the examples. Okay, how do we deal with the examples? Let us see one by one. Here, a simple example let me take. Let us see, find a matrix A. Okay, find a matrix A such that we have to find out W is in call A. W is equal to call A. We have to find out a matrix A. So here W is given by some 6A minus B, A plus B, and minus 7A, such that your A and B are real numbers. Okay, so this is how the W is defined as. Now first we will write our W as a linear combination of A and B. Okay, as we have now focusing on the linear combination, because the column space is nothing but what? It is a linear combination of the columns present in the given matrix, right? Therefore, let me write this now W as first. First, let us write, we write W as, we write our W as the set of linear combinations. Okay, set of linear combinations. Set of linear combinations. So here our W is nothing but, your W is nothing but, if you observe here, we have got A terms and also we have got a terms involved B. So what I will do is I will try to write it this way, like say this I can write it as A into. So in the first term, A is associated with the coefficient 6. I'll write here 6. B in the second row, it is like 1 is the coefficient of A. And in the third row, we have a coefficient of A as -7. All right. Plus in the first, again, now B into, if you see in the first row, we have -1 as the coefficient of B. And in the second row, we have again 1 is the coefficient of B. And in the third row, this is free from B. So I'll write here 0. There is no coefficient of B, such that your A and B are in R. They are coming from real love. Now, if you see, by substituting the value of A and B, if I substitute A and B as any different values, I'll be getting infinitely many such linear combinations. All right. So if I just change A as 1, B as 1, I'll get one set of linear combination, A as -1, B as -1, or B as some 3. Just change the value of A and B. You'll be getting, because A and B are any real number. So I'll be getting what? Many such linear combination. So I said this is nothing but set of all possible linear combination of these vectors, right? These vectors. So therefore, this is nothing but what? This is nothing but a span of these vectors. 6, 1, -7, and -1, 1, 0. Okay. So this is nothing but span of these two vectors. So now you know that we are going to use this particular this is the first step what we have done, and the second step is what we have now we are going to use this. See, these are the vectors. Since we use these spanning vectors set as the columns of our A. That's what is the definition says. The set of the vectors in these spanning sets are the columns of our matrix A. So let us write now the matrix A, which is required one. This is the column, say 6, 1, -7, and -1, 1, 0. So this is our required matrix A. Okay. So therefore, now we have arrived that W is equal to call A as desired. Okay. So these are the steps which we need to follow. So basically what we did, the column space of M cross N matrix A is all of in Rm. If and only if your Ax equal to B has a solution for each B in Rm. Okay, so that means what is the necessary condition to say that it is the I mean, the column space of a matrix is all are in Rm. For example, if you see, this is like, if you observe, this is like a 3 cross 2 matrix. Okay, so it's a 3 cross 2 matrix, and we have got here two particular vectors which are in R3. Okay, so therefore the column space of a matrix, this is possible, as I told you, this is possible only when this Ax equal to B has a solution. Okay, so if the system has to be it should have a solution, it should be a consistent system. If it has no solutions, then there is no linear combination, and there is no linear combination leads to no spanning, and then there is no spanning implies there is no call space which we can define. So therefore they're all connected. Okay, so it's very important for our understanding. All right, now let us see another example where I'm going to talk about the like whether it is in the call space or in the null space. Let's see this example where they have given us that let a equal to say 2, 4, -2, 1, and -2, -5, 7, 3, then 3, 7, -8, 6. Yeah. So here the question is, this is a given A. Question is if the first one, if the column space, if the column space of A is a subspace of Rk, then what is K? What is K? This is first question. Let us try to answer the first question, and then I think we will go for the second question. So here, if you observe the column space of A is a subspace of Rk. Here they're asking the K and what is the value of the K. So as we know that just now we have discussed the theorem that the column space of a M cross N matrix, obviously this is a 3 cross 4 matrix. Okay, 3 cross 4 matrix. So the column space of any M cross N matrix A is a subspace of Rm. Rm means I told you the number of rows. All right. So now, if in this case, what happens? The columns of the column of this A each of have 3 entries, right? In each column, if you observe carefully, we have got 3 entries, right? So here in this column we have 3 entries, 3 entries, 3 entries, right? So each column has a 3 entries. All right. So therefore the call A is a subspace of Rk. Rk means what? The 3 entries means it should be a subspace of R3. Okay, the call space, the answer for this question is the call A, or for a call A, each column has three entries, three entries. So if it has three entries, it implies the call A is, therefore the call A is the subspace. It is the subspace of R3. So if you observe here, in place of RK, we have R3. Therefore, what is the value of K? K is equal to 3. That is the answer for the first question. And the second question is, if the null space, if the null space of A, capital A, is a subspace of Rk, is it this is the next question. Is our null space is a subspace of Rk? Okay, so that's the I mean, like, the next question. So now we know that our null space is a subspace of Rn. Okay, so as we know that whenever you have got a m cross n matrix, your call space is a subspace of Rm, whereas your null space is a subspace of Rn. Okay, so here in this case, vectors, we need a vector, to answer this question. We need here a vector, we need a vector x such that a into x is defined, right? A into x is defined. So in order to define A into x, in order to multiply this, if you observe, this is a 3 cross 4 matrix. To multiply this matrix with any matrix, I should have 4 cross P, where P may be any number. Okay, so at least it should have 4 rows. So therefore, I should have, it must have a 4 entries. To define this, it must have 4 entries. Okay, 4 entries. So therefore, so the null A, is subspace of Rk. It is a subspace of Rk. Okay, but what should be K should be here? K should be equal to 4. K should be equal to 4. That's why we always say, whenever the column space comes, we will look at the number of rows here. And whenever the null space comes, we have to look at the number of columns here. Okay. So please remember this, and accordingly, we will be solving the examples. Okay. So now let us see with the same, I think, example. Let me take out the another set of, problem. How do we solve with the same matrix which is given? What we do is, we will try to find out a non-zero call vector. Okay, let us see the same matrix I'm considering, and I'm trying to find out the non-zero vectors in a call A and a non-zero vectors in a null A. How do we deal with these particular examples? Okay, with the same matrices, for a same given matrices, how do we approach to a null and call A separately? Let us try to understand that. Okay, I think with that you will be having an idea how to approach to the given problem. All right, so now let's see. The question here is, they ask us to find out a non-zero vector both in null A and call A. Okay, so basically, guys, it is quite easy to find out the vectors in the call A. Okay, because as I told you, you know that it is a linear combination of the columns of the given matrix, right? So therefore, when they ask you to find out any non-zero vectors in the call A, any particular column, if you consider, whether you take a first column, second column, third, or the fourth column, depends on how many columns it has, your matrix has. So every column will be in a call A. Okay, so therefore it is easy, quite easy, straightforward answer for a call A. It is easy. You can say that any columns of A, okay, for a matrix, any columns of a given matrix A will be in call A. Okay, will be in column. All right. Only except if, for example, any column is a 0, 0, 0 here. So they're asking you non-zero particularly, then you can leave that particular column. But of course, whenever they ask you to find out a non-zero vector in a col A, it is any column belongs to that particular matrix will become the vector in the col A. All right. So now the next question is we need to find out the non-zero vector in the null A. All right. So here it's quite hectic. We need to do the row transformations. Okay. So we have to do the row transformations here that to find out the non-zero vectors in a null A. Obviously, because you know that we have null A is nothing but we have to find out a solution for this particular equation Ax equal to 0. All the solutions which obeys this particular, I mean, like, all those X which satisfies this particular condition will be the vectors in null A, right? So therefore it is nothing but what we have to consider now, the argument matrix with A with 0. So we have to start with the row operations here simply. I think I'll just try to do the row operations, and we will be, I'll be assuming that we have already done the row operations many times. So I think I'll directly also use this. Yeah, this is our augmented matrix A along with the 0. Okay, so if you observe carefully here, I have to use then in order to use the R1, see, here what I'll do is I'll try to make this row 0 and this row 0 by using this R1. So therefore our row operation must be R2 changes to R2 plus R1, and R3 changes to, here it is 3 and here it is 2. So simply multiply this with 2 and this with 3. So R3 changes to 2 times of R3 minus 3 times of R1. Okay. So here we'll be getting, we're obtaining here this as 2, 4 minus 2, 1, 0, as we are not doing any changes in the R1. So this is 0 here. So minus 5, simply minus 5 plus 4, which is equal to minus 1, and 7 minus 2, that is 5, then 2, 3 plus 1, which is it's a plus, right? So, yeah, so it is 4, and then it is 0. And similarly this row, after multiplying this with the 3 and this with the 2, this will be getting 0 here, and this with the 2, it is 14 minus 12, right? So this will be again 2 here, this will be 10, sorry, negative 10, 9 and 0. Okay, so likewise just prepare the row, I mean, like, row transformation again. If you observe carefully, like what I'll do now, I'll just take this, I'll try to take 2 out from this particular row, that is R3 changes to 1 by 2 times of R3 in order to make that easy for further calculations. Okay, so this is like 0 minus 1, 5, 4, 0. So quite lengthy for finding out the non-zero row in null A, guys. So it is, you have to follow the row echelon form, and then you have to do all the calculations properly. Okay, now you have to continue with this row transformation, use R2 in order to make this element 0, and then, like, I'll finally, I'm after doing all the subsequent row transformation, I think finally I'll be getting achieving this particular row here. Please do the in between calculations. You will get this 0, 1, 0. I'm trying to reduce it in a reduced echelon form. Okay, so where every leading element will be equal to 1, and other than the leading element, the below and above elements will be 0. Okay, that's what is our final achievement, right? So here, if you observe carefully, now we are in a position that here is the pivot position and below elements are 0. Next pivot position is here, above and below elements are 0. So this should be our next pivot position, which is 0, since, like, we can just shift here. And also you can, if you want, if, for example, if you want, you can make this element still 0, but I think we are good with it. Now what we do, we are actually finding out the solution here. So in order to find out a solution, what I'll do, I'll try to write this in terms of, as you see, this one and this one is having a pivot position, means here we have a basic variables, right? So therefore it is like having 1, 2, 3, 4 columns. So therefore we have got a basic uh, sorry, we have got the two basic variables, and from here we have got x4 equal to 0, so we have got a value of that, and so I think we have got one free variable, that is x3. So let us try to write it in terms of a solution. So here it is x1 plus 9x3, because this is x2, this is x3, and this is x4, it is equal to 0, so therefore this is 0. And since x3 is free variable, I can write this as x1 equal to minus 9x3. Okay, and similarly here we have got x2 minus 5x4 equal to 0. As you see from here, x4 is equal to 0, right? So x4 equal to 0 means what I'll get here, like say from here, x2 and 0. Oh, I'm sorry, it should be -5 here. I'm sorry, it should be -5 here, and it is 0 here. I'm sorry, please make a note. This is -5 here. So therefore what I give, x2 minus 5x3 equal to 0, and from here it is x4 equal to 0. All right, so therefore what I get here, x2 is equal to 5x3, and here x3 is free, and x4 is equal to 0. All right, so therefore we have got the solution as, if you see, let me erase here some, let me, yeah, let me erase some part of it here and write the solution as, yeah, if I write the solution as, okay, so x, which is our x is equal to, say, x1, x2, x3, x4. This is nothing but your x1 is minus 9x3, and x2 is 5x3, and x3 is free, and x4 is what, 0. Okay, so therefore this we can write it as x3 into minus 9 5 1 0. Okay, so here this x3 is a free variable, so by choosing this x3 as any value, you will be getting infinitely many vectors. So therefore one of the non-zero vectors in the null A is minus 9 5 1 0, by taking x3 equal to 1. So we got one of the nine non-zero vector. Okay, so likewise you can get infinitely many by substituting x3 value as different scalars. Okay, so what is the basic idea here in finding the non-zero vectors in the null and call A? So when you want the non-zero vectors in the call A, simply choose the non-zero vectors. Okay, any non-zero vectors, any non-zero column of a given matrix, that will be sufficient to tell that it is in the call A. Whereas in order to find out a null A, we need to find out a solution for Ax is equal to 0, which is basically a matrix A augmented with 0, and then you will be doing a row transformation, convert them into a reduced echelon form. Once you do that, then you'll be writing it in a solution format. Okay, where you'll be getting the vectors in order with the free variables. So as you go on putting the value for a scalar, you'll be getting different vectors, right? So that will decide the non-zero vectors in the null A. Okay, this is how you'll be doing. So as we change the x3 value, the weights, okay, you'll be getting what, many non-zero vectors in the null A. All right, so I think one example, let me give you all. So please, you all have to try that, and then I think you can get back to me with the answers in the comments. So let me give you a simple example. My question is, just try this. I'm giving you with the same A as a previous example. Okay, the same A I'm giving you. But you have to consider u as, let us see, I'm giving you as 3 minus 2 minus 1 is 0. Let me write my A also, because if you miss it, 2 4 minus 2 1, and minus 2 minus 5 7 3, and this is 3 7 minus 8 6. Okay, so this is our matrix A, and let u is this, and I'm giving you v also. Let v is say 3 1 3 -1 3. Okay, so yeah, we have got a u and we have got a v. The question here is, determine if u is in null A? Is it in a null A? Could, next question is, could U be in call A? Please think about it, okay? My question is whether this U is in null of A, okay? So think about it. To be in a null of A, what are the conditions I told? And it is a 3 cross 4 matrix. So what has to be the order of the U to in order to be in null A? All that thinking you have to do. And also the same U, is it in call A? Also, I just now explained what is the basic requirement to the given vector should be in a call A. All right, whether that satisfied by the U, that is the next question. Similarly, the B question is determine if V is in call A. V is in call A. This is one thing. Could V be in null A? Could we be in null A? So it's a simple and interesting question, guys. I think I expect some answers from you. Just I'll give you a hint for B also. Whether you have to check now for B, whether it is in a call A. I told you in order to check for a B to be a call A, you need to check. I just give a hint. You have to take A with V, because A with V, argument A with V, okay, and then if you find out that your system, like usually it is what it is, like AX is equal to V, right? When I multiply the given matrix A with some vector X, I should get V. Then I can say that the V is in a call A. So for this, you need to check A argument with V and find out whether you will get a solution or the system is consistent or not. If that is the case, then you can say that as in a call A. Then the second question is little again tricky. Could V be in null A? Again, just see the order of the V and decide whether it can be null A or not. If yes, how? If no, why? So both answers you should give me in the comments, okay? So I think this is for in this video. This is all in this video, guys. Maybe in the next video we'll come up with the next topics and next interesting discussions. I think till then, take care, guys. See you all in the next class, okay, with the different concepts and different like discussions. All right, so bye bye then. Bye bye then. I think we will see you all in the next video.